talk before the break, giving 2 case studies of asteroids that have been studied by radar that either have been or have been repeatedly posed as mission targets. Slide advances, that'd be nice. There we go. Thank you. So the first case study is Toutatis, which Lance already mentioned a fair bit about. It's close to, but not quite in, a 4-to-1 orbital resonance with Earth. Can you just advance the slide, please? The clicker appears to be worked. Okay. So this is work led by Steve Oster and Scott Hudson in the 1990s. See here radar images from Arecibo and Goldstone, arranged as in Lance's previous talk. From that, derive the shape model, 4.5 kilometers long, elongated, bifurcated shape, and this complex non-principal axis spin state. That last is particularly interesting because it potentially gives us insight into Toutatis' internal structure. The evolution of that spin state depends on the asteroid's moments of inertia. So if we get a good enough shape model and a good enough spin state model, we can see the extent, or at least constrain the extent, of any density variations in Toutatis' interior. Okay, now that clears me. But there should be a plot here, and it is not appearing. This is awkward. So we have more data on Toutatis from 2000, 04, and 08. And what this should be showing you here is that Toutatis' angular momentum is changing with time. It's getting torqued around by gravitational tides from the sun and from the Earth. Most notably during the 2004 flyby, which was the closest of the set, Toutatis was only a few lunar distances away. And it got spun down by about 1 part in 1,000 of its total angular momentum over a span of a few days. Now that we have more data on Toutatis from observations in 2012, we can say that the asteroid's spin state is affected not just by the sun and the Earth, as you see here spiking at that close approach in 04, but also by the moon, which becomes important in that it is actually not in the same direction to Toutatis as the Earth is, when Toutatis is only 3 lunar distances away. And we've even included tidal torques from Jupiter, which aren't significant by themselves, but influence how Toutatis reacts to the gravitational environment it's encountering later on. This is pretty unusual dynamics. You can see the effect of the moon torquing something around from 1 million kilometers away. But we have now a completely good understanding of Toutatis' spin state from the radar data. 2012 was our last opportunity to observe Toutatis at this current set of close approaches. We see here radar images, which probably show up better on the screens in the back for those of you who can see them. As Lance said, the old radar-derived shape model, we now can see it has some artifacts from lack of coverage and our shape modeling process. The big end is significantly more angular than it actually, the actual object than it appears in our old 3D prints. And you can see many of the smaller scale surface features. In particular, you can chart out features that correspond to those we see in the spacecraft imaging from Chang'e 2. Those little bright clumps Lance was mentioning, you see a couple here and here on the little end. They correspond to these blocks here and here in the spacecraft imagery. So comparing the spacecraft data and the radar data, the radar-derived spin state model is quite good. We predicted Toutatis' orientation at the time of the spacecraft flyby quite well. The radar trajectory model was excellent, within a couple hundred meters on an object 4.5 kilometers long, which allowed Chang'e 2 to be flown approximately there, 1 kilometer from the nearest part of the asteroid's surface at closest approach. Now, there's some artifacts, again, in the radar shape modeling process, which need work. Due to the ambiguities in the radar data, we may not be able to get rid of all of them. But we can definitely say that the radar and spacecraft see many of the same surface features, and we are interpreting those features correctly. So Lance talked about how radar data can be comparable to a spacecraft flyby. Here we have radar data and a spacecraft flyby. The results aren't identical, but in many ways they're complementary. The radar doesn't get such fine resolution as Chang'e 2 got over this part of the surface, Toutatis, but Chang'e 2 didn't get the detailed spin dynamics that we see with the radar. Second case study is not yet a radar target, but is not yet a mission target, but keeps getting proposed as one since the radar observations. This is 2008 EV5, which Carrie Nugent will be talking about a bit in the next talk as well. I'll get to that. So EV5 was discovered in the early part of 2008, flew by in December of 2008, observed with radar from Arecibo, Goldstone, and also with Green Bank and the Very Long Baseline Array. The last two are receiving transmissions from Arecibo, very useful in resolving ambiguities in the spin state of the object. You see here, delayed operator images again. You'll notice they're all roughly similar in appearance. EV5 is approximately spheroidal, but you can notice there's some surface features such as this concavity, which you see rotating across the surface of the object. We do the shape inversion process. We get a shape model that looks like this, 400-meter spheroid with this equator-aligned ridge, which is interpreted to be due to York radiation pressure torques in a past episode of rapid rotation. The object bulged out around the equator. Whether the concavity up here is an impact crater or just reflects the arrangements of blocks on the rubble pile as it rearranged itself, it's not clear with this resolution. As a caveat, we didn't see the North Pole. We were just slightly to the south of the equator. So our shape model is pretty good in here, but doesn't really constrain the topography there directly. Now, I'm afraid it barely shows up at all because the color stretch on this screen is pretty lousy. It should show up fine on the monitors there. There is a feature right there. How many of you can actually see that dot on this monitor? Okay, thank you. So there's a single bright pixel that shows up right here, quite a ways behind the trailing edge of the echo. So effectively, we're seeing some small feature on the surface. This is 7.5-meter resolution here, so it's about 10 meters across, given they're only seeing the front side of it. But sticking up far enough around its surroundings to be visible well past the terminator. And we can track features like that, and a few other spots in here, through quite a bit of rotation. That's a boulder on EV5 surface, just one that isn't resolved. Based on the presence of less than 10-meter scale boulders on EV5 surface and radar scattering properties that indicate it has a fair degree of fine-grained regolith, there have been lots of mission proposals to go to EV5, particularly focused on collecting samples. Why are the most important pictures in my talk not showing up? They worked fine on the import. This is weird. There should be a picture here of the Marco Polo R spacecraft, which was proposed to ESA through the M3 mission, made it to the final stages of down select. In February of this year, ESA elected to not pursue the mission. Marco Polo R would have gone to EV5, touched down on the surface, touch and go sampling, picked up material, returned it to the Earth for analysis, taking advantage of EV5's orbit being differing from that of the Earth by 1/15th of a year. So it comes near the Earth in 2008, loops back around, comes by again in the mid-2020s, and then again in the late 2030s. Marco Polo R would have taken advantage of the 2024 or close approach to have short mission duration going out and coming back. Unfortunately, ESA is elected to not pursue the mission at this time, so Marco Polo R may be reproposed. We'll have to find a new target for it. EV5 has been talked about as a target for human missions to deep space. You have here the NHATS chart. Again, mission stuff in 2024 and again in 2039. Velocity requirements from LEO isn't too bad. It is a year-round trip, which may be a bit more than you'd want to try, at least for a first human asteroid deep space mission. But it is on the list because it's one of the most accessible objects that is so well characterized. For that same reason, it is on the list, the short list for the ARM pick up a rock version, where you pick up a 30 to 45-ton boulder from EV5 and return to Earth, Moon, space. Launch again would be 2019, 2022 or so. Return to Earth in the mid to late 2020s. And you see here a graphic that Paul Lavelle was happy to provide. EV5, Bennu, and Itokawa are the three favorite targets for that because they're all relatively accessible, and we know there's boulders on their surface. And EV5 is the most accessible of the lot. So should NASA elect to pursue the pick-up-a-rock version of ARM, EV5 is is probably one of the preferred targets right now. Again, NASA decision on ARM is pending, so we'll see what happens. But an illustration of how detailed radar data really plays forward into planning missions. That's what I've got. Nothing? Wow. Oh, okay.
Alessandra Springman, Arecibo Observatory. Which of these targets would you like to send a mission to personally?
EV5, because it's really, really hard to get to Toutatis and stop. Tonga 2 went past Toutatis at just under 11 kilometers per second, which means we still don't know the mass of Toutatis, because when you're flying by an object at 11 kilometers per second, even if you're only skimming the surface of an object a few kilometers wide, you don't actually get a meaningful deflection. So we have no idea of Toutatis' mass. EV5 is a lot easier to get to and stop once you get there. Oh, Lance is raising his hand.
No, not a problem at all. Just wanted you to comment on some of the data we haven't analyzed in detail yet, in particular the potential for polarimetry, what that might tell us.
Yes, okay. So one of the questions for spacecraft mission planning, in particular samples, is the block size on any individual part of the surface. We can't, from the radar data, we can constrain the size of 2 centimeter scale blocks based on the radar scattering properties of the surface. How much reflection there is at the multiple bounds and single scattering at the radar wavelength scale. To do that, we have to take each radar image, make a shape model, and then map the polarization properties of the radar reflections over the surface of that shape model. That's something that we haven't done for EV5. It could be done. Some work on Bennu for OSIRIS-REx shows that we do expect to see some variation, but it's not clear exactly what that implies in terms of surface properties, other than that there is some variation.